Okay, so we are continuing section 8.5 power series. We looked at a few examples, and now we're going to look at another example. So let me give you a moment to copy the example down, and we will proceed then. Okay, so let's see here. Let's see. So we want to find the radius of convergence and the interval of convergence of the power series, of this interesting power series. And of course, class, we need to use the ratio test, just like we did on the previous power series, to help us. So this particular power series, when we use the ratio test, hold on, I always have to adjust the font. The default is 5 point, but it's just too fat for our purposes. Yeah, this here is a sub n. So, okay, we proceed to use the ratio test. What we're going to try to do is determine some interval over on the x-axis over which this power series converges. And then we will test the endpoints as well of that interval. So, okay, here we go. So here is our nth term, which is -1 to the nth power times x minus 3 to the nth power divided by 2n plus 1. And we're going to look at the limit of the ratio of the n plus first term to the nth term, and let n goes to infinity. So the computation is, the way we compute this is just like you've seen before. Here is the nth term. And here is the top fraction is the n plus first term. So we're going to take the top fraction and multiply it by the reciprocal of the bottom fraction, group like terms together, and compute the expression. Let me just give you a moment to copy this down. I mean, I think I don't want to just talk, you know. I think you understand what you see here in front of you, but let me know if you have any questions, okay? And let me give you a few moments to copy it down before we proceed. While you're copying, I'll just mention too that, power series have applications in engineering. They talk about what's called a Bessel function in example 3 in the textbook. And they have next to the example a figure that talks about how the Bessel function can be it's a power series. It can be used to uh, model the vibrating member. I'm sorry. The Bessel function can be used um, to create a computer generated model for a vibrating a rubber membrane. That's example 3 in your book. So I think that's worth. It's a nice example, and it shows an application of a power series. A Bessel function is a power series. Okay, all right, great. So all right, we do the computation, and we end up getting this limit here, and the 2n plus 1 over 2n plus 3, okay, that is always positive, so that can be brought out in front of the absolute value sign, but the x minus 3 has to stay inside. But what's the limit? This 2n plus 1 over 2n plus 3, if we let n go to infinity, well, let me just let n go to infinity. Okay, you have 2n plus 1 over 2n plus 3. Okay, let me just what I'm doing here is I'm doing a little, I'm trying to justify this 2n plus 1 over 2n plus 3 goes to 1 as n goes to infinity. And intuitively, you can see that because as n is large, the 1 and the 3 don't contribute much, don't really contribute, right? Their effect is minimal. But if you do it algebraically, which I'm showing on the left here, you can very clearly see by rewriting the fraction, that as n goes to infinity, the limit of 2n plus 1 over 2n plus 3 does equal 1. Okay, and so the limiting ratio is the absolute value of x minus 3. Is it helpful when I add this extra little step in here? Is that helpful, what I'm showing here, to justify why Okay, good, good. Wonderful. Okay, great. Thank you, Javier. Thank you, Taj. Thank you, Ange. Um, all right. So now we get this absolute value of x minus 3. And what do we want to do with the absolute value of x minus 3? What do we want to do with that limiting ratio in order to help us find the interval of convergence? What's the ratio test say? For convergence that you need, I mean, this here is L, right? This is L. What do we want L to be less than? That's right, Taj. We want L to be less than 1. So that's what we're going to do. We're going to be solving this inequality here. Okay. So are there any questions before I move to the next page? All right. Let's proceed on then. So this is just a summary of what I just spoke about. By the ratio test, the series converges when the absolute value of x minus 3 is less than 1. Okay, well, if the absolute value of x minus 3 is less than 1, maybe I can put that above here, absolute value of x minus 3 less than 1, that means then that x minus 3 is between -1 and 1. And that inequality becomes that x is between 2 and 4. So our series will converge when x is between 2 and 4. But the question is, are there any more x values where our power series converges? And that means we need to test the endpoints. But let me let you get caught up here. Please let me know if you have any questions. Okay, so, one thing I like to do is say, okay, well, all right, I mean, if the limiting ratio equals 1, we know in the ratio test, we know the ratio test would give no information. Well, that would happen when either x equals 2 or x equals 4. Because, like, for instance, the absolute value of 2 minus 3 is the absolute value of -1, which is 1. Okay, the absolute value of 4 minus 3 equals 1 also. So the ratio test gives no information when x equals 2 or x equals 4. But just because the ratio test gives no information doesn't mean that the power series is going to diverge at those x values. We don't know. The power series could converge at those x values, or it might just converge at one of the x values. The only way we can figure that out is to manually check. We have to substitute in x equals 2 into the power series, and then substitute x equals 4 into the power series. And obviously, we do it one at a time. So let's go ahead and substitute in x equals 2 into the power series. That's what I have on the next page. Okay, so we have to manually check. Again, like I said, we have to manually check here. So when x equals 2, we substitute x equals 2 in the power series. Okay, so, and then we compute the resulting series. Let me give you a moment to catch up. I don't like to generally talk while you're copying notes. I kind of like you to get caught up a little bit, and then I can talk, you know. I just feel better that way. But let me know if you have any questions, okay? Let me know if you have any questions. Okay, and I'll make a comment over here. So over here, we have negative 1 to the nth times negative 1 to the nth power. So, you know, negative 1 to the nth times negative 1 to the nth is equal to negative 1 to the n plus n power, right? We add the exponents. So that's negative 1 to the 2nth power. Okay, and 2n is even power. That's an even power, right? So and negative 1 to any even power equals 1. You know, I mean, if you had, you know, negative 1 squared, that equals 1. Negative 1 to the 4th equals 1. And so forth. So see, 2 to the nth power, no matter what n is, and 2 to the nth power is going to be an even number. 2 times 1 is 2. 2 times 2 is 3. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, and so forth. So, you know, so that's how we get the 1 here. And so the power series becomes this series at when x equals, power series becomes this series when x equals 2. And, oh, what does that series do? Does it converge or diverge? Well, we're going to use the limit comparison test. We're going to let a sub n equal 1 over 2n plus 1, obviously. Okay, and we'll let b sub n be 1 over n. Okay, so I'm going to really do a limit comparison test of this series with the harmonic series. Well, all right, the ratio here of the an to bn will be equal to the limit as n goes to infinity of n over 2n plus 1. But that limit will just equal a half. And so because the ratio of the terms gives you a constant that's positive, that means our power series that has to diverge at x equals 2 because the harmonic series diverges. So basically what you're saying is that our series here at x equals 2, the series, once again, is the series starting from n equals 0 to infinity of 1 over 2n plus 1. That series, the terms of that series in the limit become proportional to the terms of a harmonic series. As a matter of fact, the terms of our series, as n gets large, are essentially going to be 1/2 times the terms of a harmonic series. Well, 1/2 of infinity is infinity. So the fact that the harmonic series diverges means our series has to diverge. And so therefore, our power series diverges at x equals 2. Are there any questions on that? Okay, let's proceed. Let's proceed. Now we need to test the power series out when x equals -2. And we do this here. I'm sorry, at x equals 4. I'm sorry, x equals 4. So at x equals 4, here, there we substitute in 4 for x. 4 minus 3 is 1. Now, sorry here, let me just get this thing off. I don't know why it, hold on, I want to, there we go. Let me see one thing here. Right, so this 1 over nth power is just equal to 1, right? And so we end up getting the series from n equals 0 to infinity of -1 to the nth power over 2 times n plus 1. That series converges by the alternating series test. So like there, b sub n would be 1 over 2n plus 1. Okay, so like using the alternating series test on this alternating series, b sub n is 1 over 2n plus 1. And that that means that the terms of the series, well, they're not disregarding the plus or minus part. The terms of the series of that alternating series are getting smaller with n, so they're decreasing, and they're approaching 0. And it's obvious, basically, and that's true. And so by the alternating series test, this power series here it converges. I'm sorry, this series, alternating series, converges. So our power series converges at x equals 4, and now we have established what the interval of convergence is. The interval of convergence goes from 2 to 4, but it does not include the endpoint x equals 2, but it does include the endpoint x equals 4. So that's an example where one endpoint, the left part of your interval is open, the right part of your interval is closed. And that's, of course, a interval with length 2, so radius of convergence is half of that, which is 1. Okay, are there any questions on that? Who feels comfortable with so far with what they've learned today, or at least somewhat comfortable? You maybe don't have to be perfectly comfortable, but okay, Ange is reasonably comfortable. Nathaniel and Tosh, okay. Ethan, good. And Mario, somewhat. All right. Kittis, how do you feel? How do you feel? Are you more or less comfortable? Okay. All right. All right. Good. Good. All right. Sansar, how do you feel? So I'm trying to call on students that maybe I don't always call on. A little confused. Okay. All right. All right. Well, is anything I can elaborate on, or you just need to practice a little bit? What you're thinking? Any questions I can? The bracket for 4. Okay. So when x was equal to 4. Okay, when x was equal to 4, and we substituted 4 in the power series, we got an alternating series here. We got this alternating series. And this alternating series converges the series n equals 0 to infinity of -1 to the nth power over 2n plus 1. That alternating series converges by the alternating series test. So because of that, our power series, our power series becomes this series, this alternating series at x equals 4. And because that alternating series converges, that means our power series has to converge at x equals 4, which is why we include x equals 4 in the interval. That's the purpose of the closed bracket. That's the purpose of this closed bracket here, to say that 4 is included as one of the x values where our power series converges. Okay, excellent, excellent. Of course, and at x equals 2, the power series doesn't converge there. Okay, all right, you're welcome, you're welcome. So we can always ask now, I mean, are there any other x values that the power series could converge at that we need to worry about? And the answer is no. I'll just show you this. I think it's probably good just to mention it once. There are no other values of x for which the power series would converge. Let's think about the ratio test. So we looked at the ratio test where our limiting ratio was less than 1, and based on that, we came up with an interval of x values where the power series converged. And then we test the endpoints of that interval, because those endpoints are where the ratio test equals 1, gives you a value of 1. and the ratio test is uninformative. But now if we also think about the ratio being greater than 1, oh, do we have to worry about that? The answer is no, because the ratio test says that when the limiting ratio is greater than 1, our power series would diverge there. Well, if absolute value of x minus 3 is greater than 1, that means x minus 3 is greater than 1, or x minus 3 is less than negative 1. Okay, either of those inequalities would satisfy the absolute value of x minus 3 being greater than 1. Well, if x minus 3 is greater than 1, that means x is greater than 4. And if x minus 3 is less than negative 1, that means x is less than 2. So our power series would diverge when x is greater than 4 or x is less than 2. So basically, we've accounted now for all the possible x values on the x-axis. This part here, this last part here on this page where, I have the note, right? This here is like, this is not necessary to do in order to get the answer, because but I'm just trying to sort of tell you why, when we use the ratio test, why we only need to worry about two things. Where does the limiting ratio, where is it less than 1? Okay, find the x values for when the limiting ratio is less than 1 for the ratio test. And then once you have that interval, look at the endpoints and manually check those. Okay, and then you don't need to worry about any other x values. Okay. All right, so just trying to be complete here. Are there any questions on this? Okay. It's really a very beautiful subject, these power series. And again, ultimately, we want to take functions and express them as power series. So where the power series converge, what x values power series converge for, is important, because if we take a function of x and express it as a power series, the power series representation is only good for the values of x where the power series converges. And you're going to see probably some of the most, you're going to see some beautiful math coming up. I mean, all this math is great, right? But you're really going to see some cool stuff. On Thursday, we're going to talk about section 8.6, where we can take power series and actually write them as a function. Well, we can take a function and write it as a power series. So we're going to start our discussion on that. All right. Well, if we're good, I'll stop the recording. Are there any questions? Okay. Excellent.